Hello. Today we are going to be looking at can you planet? And so what we're going to do is we are going to be looking at the different planets and seeing all kinds of things. So let's look at our purpose here. Our real question that we're looking at is how we can classify the 8 planets. And when I say classify, that means put them into groups. How can we group them? I know that we've talked about inner and outer planets, but we can also group them in different ways. And with this lesson, we are going to practice reading tables and charts to learn about various aspects of the planets and their relationships with one another. And I know it says and, but that and is, we're not doing that other part. So we're just going to be doing that. And really, what we're doing here is analyzing data. We're going to be looking at some charts of some information and analyzing this data or understanding what those numbers mean because that's what scientists do. They look at information and then they think about it and use that information. So let's do some of this together so that you can practice and it can help you understand what I'm asking you to do on your assignment. So let's go ahead and check this out. So we have our Can You Planet chart. And I'm going to make myself a little bit bigger. Hello. We have our Can You Planet chart. And you have to see my shirt, by the way, before I start. Can you tell what it is? It's the sun, and then the one, two, three, four, five, six, seven, 8 planets. And look who's left out. Poor Pluto. All right. Sorry, I had to show you before we get started. Okay, so let's go ahead and look at this chart. So it has all of the planets at the top. I can see it says planet, the diameter. We've talked about that before. Some students asked me, and I showed them, when you talk about a circle has from the center to one side, we call that a radius. But if you do it all the way across, that is the diameter. But when we're talking about our planets, we're talking about spheres. So, you have to think about like if you were to like fruit ninja slice it, any kind of sphere in half and then measure across from the center. That is what we would have here for um, our diameter. So really, we're thinking about it in terms of size. So you can see the size of all of those, and they are in kilometers. And then the next column is the approximate period of rotation. So remember, when we talk about rotation, that means it's spinning on its axis and how long it takes to spin on its axis one time. We know on Earth it takes 24 hours. Right here it says 23 hours, 56 minutes. But I guess we must round it up a little bit to 24 hours. And, that is our day, one day on Earth. But all of these planets have different patterns of rotation. So we're going to look at that. If they have moons or rings around them. So we're looking at all of these planetary facts and kind of comparing them. So let's look here first at Earth. Earth, I can see, is 12,800 kilometers. And I'm going to use my little um, tool here, I think, so I can draw. Oops. Hang on a second. All right, I think I figured out what I'm going to do here. But let's go ahead and look at Earth. And Earth, I can see, ooh, that's not going to work. Ooh, let's see. I thought I had the pointer turned on, but I didn't. Okay, here it is. So Earth is 12,800 kilometers across. That's its diameter. When you look at these numbers here, which planets are larger than Earth? So which planets are larger than 12,800 kilometers? Go ahead and look. All right, first of all, let's see. Do any of the inner planets, are any of them larger than Earth? Mercury's not. Venus is not. Okay, there's Earth. Mars is not. Okay, so none of the inner planets are larger than Earth. Well, whoa, Jupiter is. Jupiter's larger. Saturn's larger. Uranus is larger. And Neptune is larger. Okay, so all of the outer planets are larger than Earth. Okay. Now, looking at these planet sizes, which two are really similar in size? Which two are similar in size? We've got a couple that are very similar in size, but which two would you say are similar in size? Okay, yeah, Venus and Earth. Venus and Earth are the closest in size to one another because Venus is 12,100 kilometers in size, and Earth is 700 kilometers larger in diameter. So they are really close in size. The other one that I thought was pretty close in size is Uranus and Neptune, but that is like over it's over 600 kilometers because if I added 600 kilometers to 49 500, it, it would only take me to like 50,600. So I would have to add more than 1,000. So, Venus and Earth are way closer in size than Uranus and Neptune, but they are kind of like the second place pairs. All right. So, another question I want you to look at is which planets have moons? Okay, which planets have moons? Because not all of the planets have moons. Which ones have moons? All right, and I can see the moons are right here. All right, which ones have moons? Not Mercury, not Venus. Earth does, Mars does, Jupiter does, Saturn does, Uranus, Neptune. All of these planets here have moons. So Mercury and Venus are the only two that don't have moons, and we have one moon. All the rest have more than one. Which one has the most moons? Yeah, Jupiter. Jupiter has the most moons. I mean, that's a lot. So if we added all of those up, if you added up all of the moons, how many would we have? All right, I'm going to get out my paper here. I probably should be doing this with my mental math, but I am going to do this on my own. So I've got one, two, three, four, five, six. I'm going to ask you to do this too, right? I added the one and the two for Earth and Mars. I just made it three, so I am doing this. I love to do math, and it's not just because I'm a teacher. 22 plus 3. So how many moons do we have total? All right, I have my number. I'm going to double check it. Here's my number. Let's double check it. I've got 165. Am I right? You know that we have technology these days that we can use, but it's never a bad thing to check on a calculator. Yep, 165 moons. So we have a lot of moons here. Okay. Um, and so let's go ahead and look at the periods of rotation here. Um, look at our period of rotation. We know it says 23 hours, 56 minutes. We always say that Earth is 24 hours or one day to rotate. All of these is considered their days, but we're measuring it in what kind of time we know because we understand Earth time. Um, so we're about 24 hours. It says 23 hours, 56 minutes here. When you look at these other periods of rotation, which one has about the same period of rotation as us? Which one has about the same period of rotation as us? It takes about the same amount of time. Yeah, Mars. Mars is 24 hours, 37 minutes. So it's just a little bit longer than an Earth day. But yes, Mars has about the same amount of time. Um, look at look at the other ones. Okay, so Mercury or Earth and Mars we're measuring in hours. Look at Jupiter's. 9 hours, 55 minutes. That's fast, right? So every almost 10 hours, you would have a new day. Same with Saturn, 10 hours, 39 minutes. Uranus, 17 hours, 14 minutes. Neptune, 16 hours, 7 minutes. Okay, so they all have different periods of rotation. Now I skipped. I kind of look all over the place when I look at charts, but look at Mercury. 59 days is how long it takes for it to completely spin on its axis. And Venus, 243 days. That's a long time, isn't it? So, wow. And it has these little asterisks next to them. It says length of day, sunrise to sunrise to sunrise. Um, so it's saying that that's 176 days for it to go from sunrise to sunrise, 117 days to go from sunrise to sunrise. So that's what that info is. So, what we're doing here is we're thinking about these numbers. We're not just looking at them. We're kind of thinking about them, asking questions. What other question could you ask about this? What kind of question could you ask that you could answer based on this info? All right, we're going to go ahead and look at another chart that we're going to study here, and it's got a lot of the same information. I think you've already seen it once before. Let's see. Okay, yeah, here. This is the one actually from our book. And it also has the period of rotation, but it has the first one is the period of revolution. So we're going to be looking at that period of revolution, the period of rotation. They have it set up a little different. Look, Earth and Mars, they have about 1 day. So it looks like they estimated a little bit differently. So Mercury, it says 59 days. I'm going to go back to the other chart. Oops, wrong way. Mercury is 59, Venus 243. Okay, it's about the same there. It looks like it's rounded a little bit. Okay. Ooh, temperature. The temperature is there. We didn't have that before. Number of moons we had, the density we have, and then diameter. And they also have it in miles. But okay, so it says for Mercury, 4,878 kilometers. I think that's different than what we saw before. Oh, this one's 44,900 kilometers. So this one, it looks like they rounded up. So sometimes you might see the same data, but it might be a little different. Maybe this one looks like they rounded to the nearest 100 kilometers. So we don't have exactly the exact amount. Whereas this other chart, it looks like they have it to the nearest kilometer in the ones place. So you might just see some of those differences, and that's okay. I do want to focus right here on the temperature. Let's go ahead and start with the temperature. It says that the inner planets surface range, outer planets top of the clouds. So they're telling you where they're getting that information for temperature, and it is in degrees Celsius. Look at the range here. I'm going to start with Earth because we don't really use Celsius in the United States. We use Fahrenheit. So these numbers probably don't mean the same thing to you as if they were in Fahrenheit, but we can still use this info to help us. So it says negative 88 to 58 degrees Celsius is the range in the United States. So we know that there's places in our world that are very, very cold, like Antarctica, or the Arctic Circle up by the North Pole. Those are probably those places that are getting negative 88 degrees Celsius. But then it goes all the way to 58 degrees Celsius, which could be really hot in some of those desert locations, maybe around the equator. So we know that's pretty extreme. But look at Mercury, negative 173 to 427. I think that's way too cold for us to survive and then way too hot. Same with Venus. Look at that. 462 degrees Celsius. That's a really hot. Mars, it looks like their low number is about the same as ours. It's a little less, and then -5. So it doesn't get as warm on Mars as it does here on Earth. It's always below degrees Celsius. It's always below freezing because in Celsius, 0 degrees is freezing, 100 degrees is boiling. So Mercury goes below freezing and above boiling with its temperature. Venus goes above boiling. Mars always is below freezing. And then look at the outer planets. All of those are always freezing. Oh my gosh. So, when you look at the temperature, what's the only planet besides Earth that we could possibly survive on? Just looking at temperature alone, because 100 degrees is boiling, 0 degrees in Celsius is um, freezing. So, most of these are below freezing, and some a couple above boiling. So Mars is really the only one temperature-wise that, we could survive on. It's the only one. All right, I'm gonna take a quick little break. Hang on. All right, we're gonna go ahead and talk about density for a few. A lot of students in fifth grade don't understand density, and you don't really have to know about it yet. You'll learn about it when you get into some of the higher level grades. But just looking at density here, you can see these numbers, and we can just talk about those numbers. But I'll give you kind of just a real general definition for what density it is. It's the degree of compactness of a substance. So you're thinking about how much stuff or how much is inside of something. Um, a long time ago, I used to be a lifeguard, and when I took my lifeguard training, there were some people that were very dense, and they would not float. They would sink. They were like full of muscle. They were just completely solid. They were very dense. And then me, I was a little bit more dense, and I would float. That was one of those characteristics. But you think about people's bodies. We can have density. We can talk about density in a lot of areas. But I always think about like the muscular versus not very muscular, and what it does in the water. That's kind of just what I think of. But we think about density, it's really the amount of stuff inside. And we know that those inner planets have solid cores and they're rocky. And look at the density in all of those. They have that. Um, that we're in grams, centimeters cubed, right there. So they're all very dense, like it's in the fives and the threes. And then if you look at the outer planets, you can tell that they are less dense. And we know that's probably because they are the gas giants. They're not as solid, they don't have as much stuff inside. But you're going to learn more about density when you get into some later grades in science. All right, so I saved the best for last. The period of revolution. That is the amount of time it takes for each of these planets to go around the sun. And so we're going to look just here, this little section. But before we talk about that, what shape do these planets revolve in? What shape do they revolve in? When they go around the sun, what shape is that? I've said it a couple times. Okay. Ooh, yeah, that shape is called elliptical. Okay, it's an elliptical shape. And when you think of an elliptical shape, what is that shape? It would be, oh, it's an oval shape. Yes, it's an oval shape. So, an oval shape is how the planets orbit the sun. Sometimes you're going to see a model that looks like this, and it looks completely circular. Sometimes that's because the orbit path, that elliptical shape, is not what we're looking for. Maybe we're just trying to figure out the order of the planets from this one. So just remember, sometimes models show us different things, and not every part of a model might be correct. So this one, the shape is not correct. Let me show you one that the shape is correct. This one. Okay. See how those orbit paths are more like an egg. In fact, I thought of something else that they're like this. Here, I'm going to be the sun. Okay, it's like a track. This is Grove City High School's track, and it's that elliptical shape. And if you think about the distance from the sun, even the ones that are on the inside are closest to the sun. What would that do if they all went at the same speed? Which they don't. But if they all went at the same speed, and one was closer to the sun than the other, what would happen? All right. Well, you know what? I'm going to show you because I went over to the track and did this. So let's go ahead and see that data. All right, there I am at the track. The top part is me in the inside lane, the bottom is the outside lane. And I have sped up both videos in the same exact way. So you're gonna be able to see which one takes less time for me to go around, the inside or the outside lane. What do you think? All right, the inside lane actually won. That makes sense to me because I had less distance to travel being on the inside than the outside. So I think when we look at the data, we're going to see that the inner planets are going to take less time to orbit the sun than the outer planets. Let's go see. All right. So when you looked at that, you could see that when I was closer to the center, it took me less time than when I was farther out. And we're going to see that with those revolution paths of each planet. So let's go ahead and I'm going to go back and we're going to see about those planets. So remember, elliptical path, that is an oval shape. And sometimes you're going to see models that aren't quite right for the path. Okay. You're going to see things that look like this. Wrong. Okay. Remember, they are elliptical shaped. Okay. So, all right. So, we're going to go ahead and check out the revolution periods or times in Earth days and years for each planet. So, what that means is the amount of time for each one of these planets to go around the sun. So, we know that Earth goes around the sun every 365 days, or that this is rounded a little bit, but we also say that 365 and one fourth days. Remember, if we add those one fourths up four times, we add an extra day every 4 years. That's our leap day when we have a leap year. But every time we go around the sun, that is a year. And so, something we all celebrate every time we go around the sun is our birthdays. Yes. So, every 365 days, it's your birthday on Earth. So, happy birthday. Earth birthday, right? Okay, because that we have life on Earth, right? So we have that butterfly there. Um, but how often would you have your birthday if you lived on Mercury? How often would you have your birthday? How often would you go around the sun on Mercury? How often? Happy Mercury birthday every 88 days. 88 days. That is awesome. So Mercury goes around the sun a lot faster than Earth. And think about it. They are in like the inner lane. Like I was on the inner lane on the track. Mercury is closest to the sun. So it makes sense that you go around the sun faster at Mercury. Look at Venus. How often would you have your birthday? Or how often would we go around the sun, make one revolution if you lived on Venus? It would be every 225 days. 225 days on Venus for you to have your birthday. So that's cool. We know Earth. What about Mars? What about Mars? How old, or wait, how often? 687 days. Happy birthday. If you lived on Mars, 687 is it's more than double Earth, but you would be about half the age, probably younger than you are now. So if you're 10, you would be maybe 5 if you lived on Mars. Oh, so cute. Let's see, I am almost 44, so I'd be about 22 on Mars. Okay. All right. So every 687 days, it's your birthday on Mars. What about Jupiter? How long do you have to wait for a birthday on Jupiter? How long will you wait? Because you got to get your balloons ready. You got to get everything ready for your birthday on Jupiter. Happy birthday, Jupiter. Happy Jupiter birthday. Oh, you'd have it once every 12 years. Oh, you wouldn't even be one right now? Sorry, that's kind of embarrassing, isn't it? How old would I be? Okay, so I am 44. And if I divide that by 12, how many groups of 12? Oh, I'm 3.5 on Jupiter. All right, what about Saturn? You guys would not even be one on Saturn. You're still a baby on Saturn. We're going to go with my 44. How old would I be? How many groups of 29 do I have? Oh, just about 1.5. Mrs. Allforce's birthday on Saturn. I am only, and my next birthday, I'd be 2. All right, what about Uranus? How often can we celebrate on Uranus? Oh, once every 84 years. That means you and I would not even have had a birthday yet. Neither of my parents. Oh my gosh. So you might have a first birthday on Uranus. It's 84 years. That's going to be a long time to plan for your first party, right? What about on Neptune? Oh, it's longer than our human life expectancy for it to go around the sun once. Well, we better use all these balloons because once every 165 days,
Years.
Neptune has a revolution. So you would only have your birthday once every 165 days.
Years.
That's kind of a long time to wait. So we're all babies if we lived on Neptune. All right. So I hope that you enjoyed learning to read some of these charts a little bit and obviously my goofiness because every time we go around the sun, we can celebrate our birthday, right? But I hope you enjoyed this and also learned how to analyze this data because I'm going to ask you to do some of that on your assignment. So good luck. Take care.
Happy birthday to you. Happy birthday to you. May good luck go with you. Happy birthday to you.
That's all for me. Take care. Peace.